So today our mathematician spotlight is Siddhi Krishna. She's a graduate student at Boston College, and she studies topology and knot theory and 3 and 4 manifolds. We'll hopefully talk about topology a little bit more at the end, but it's the shape of things. The shape of things that are stretchy and that you don't really care what you can do to them as long as you don't break them or like put things together that weren't together before. So the classic joke is that a donut is the same as a coffee cup, because if you take a coffee cup and you sort of shrink it and then make the handle kind of fatter, you get a donut shape. But here's some other topological things. This is a Klein bottle hat. So this is a surface with only one side. If you decided that you wanted to paint the outside a garish color of pink and the inside a garish color of orange, and you started with the pink, painting, you would find that you had already painted the whole thing before you even got to orange. So it's a really lovely hat, and it's extra super warm because it's got 2 surfaces on it. And topologists also care about things like this thing, which has 2 sides, an inside and outside, and this thing, the Mobius band, which has only the one side, and in fact only the one edge too. This guy has 2 edges, this guy has only 1 edge. So that's something about topology. Siddhi in the summers works at Beam, which is a summer program for smart inner city kids. There are a number of programs like this, and I think that Beam is one of the best because in addition to doing like math enrichment, which is great, it also does all the other things that you might want, like homework help during the year, help applying to high schools and colleges, and then teaches kids things like Rubik's Cubes and other games that they might want to know as mathematicians. Okay, so I have told you the plan for the last couple weeks of the semester, which was to learn to integrate scalar and vector valued functions over curves and surfaces. So that's been the plan. So we started out with doing scalar line integrals, which are scalar functions over curves. And then we've been talking for the past couple of days about vector functions over curves, or integrating vector fields over curves, vector line integrals. So these parts we have been doing. And pretty much now we know how to do it. So we can do this now. Yay. And today we will start learning how to integrate things over surfaces. And we won't integrate anything over surfaces today, but we'll just start setting up how you would do it. So before we do that, let's talk a bit more about conservative vector fields. And I'll tell you a trick for that today. So last time we learned that if your vector field happens to be conservative, meaning that it's a gradient vector field for some function, the gradient of some function, life is great. So recall. So recall is a dangerous word in math because you can ask someone to recall anything. Recall that awesome theorem I proved or whatever. And then you're like, oh, really? OK, if you say so. But recall from last time the fundamental theorem of line integrals, which says that if f is a gradient vector field, meaning that f can be written as the gradient of f for some little function little f, then we have a special name for this kind of vector field. So f is a conservative vector field. So this is not politically conservative. It's conservative in a physics sense, like conservation of energy, that sort of thing. It's a conservative vector field. It is path independent. So what that means is that if you have 2 curves, let's say you have a curve going from the math classroom to the lunch place, and you decide you're going to go this way because you think it's the best. Here's C1. And your friend is like, oh, I know another way. It's actually much better if you go through Parrish. So they go like this, and they take C2 to get there. That if C1 and C2 share start and end points, then the vector line integral over C1 of f dot t ds is the same as the integral over C2 of f dot t ds. if this vector field is conservative. So it means it's path independent. And if it so happens that you have some curve C is a closed curve, well, a closed curve means you start somewhere and you go around and you come back to where you start. So this vector field is path independent. It doesn't matter if you did this, or maybe if you did this, or maybe you did this, or did this, or this, or if you just didn't move. So the integral over C of f dot t ds is 0. Another way you can think of that, and this is f of the endpoint minus f of the start point when big F is the gradient of little f. So you can think about the fact that it's just f of the endpoint minus f of the start point, and they're the same. Start and end in the same place. Yeah?
These curves can intersect with themselves?
Yes, these curves could intersect with themselves as many times as they want. They don't have to be closed. This could be any curve in the plane, these C1 and C2. Yeah, you could, you could do something. You could be like, I am going, oh wait, I forgot. I dropped my pen. I'm going to go pick it up. Oh, wait. Oh, hey, yeah, I'll walk with you. Oh, no. Oh. Yeah, and that would be the same. It would be the same. This C3 would be the same also. Yeah. Good question. Yeah. And the idea of these things is that if f is a gradient vector field, one way to think about it is like f tells you how you f tells you the way to ascend most steeply on a mountain. So you can imagine that little f just like tells you your elevation when you're on a mountain. And so the gradient vector field is just telling you which way to go to climb most steeply. And so if you integrated the line integral over some curve of f dot TDS, it would be like how hard is it to hike, basically. So when you're going uphill, it would be positive hard. And if you're going downhill, it would be like negative hard. And no matter how you get from this point at the base camp to this point at the top of the mountain, you'll have done the same amount of elevation gain, even if you go up and down or whatever, or if you just sort of hike there directly. On the other hand, if you do a loop hike, you start somewhere and you do a loop, your net elevation gain is 0, no matter what. That's the idea of conservative vector fields. It's like conservation of elevation gain and loss, something like that. Yeah. So what you should be thinking now is, wow, conservative vector fields are great. I hope that all my functions will be conservative. But the unfortunate thing is that not all vector fields are conservative. So for example, some vector fields are not conservative. For example, f is negative y comma x. This is one of our favorite vector fields. This is the counterclockwise circulation vector field. And we talked about it makes sense that this is not conservative because it tells you if you follow this path, you will be climbing. If we think about our metaphor or our application of telling us where to go to climb. If you go, you'll climb, you'll climb, you'll climb. But then you get back to the same point, and it says you've been climbing that whole time. You got back to the same point, you're going to have a higher elevation to the same point you started at, which doesn't make sense. So this is not a conservative vector field. So some vector fields are not conservative, but here's the clever idea, is to break a vector field into a conservative part plus a non-conservative part. And the idea would be that life is easy on this conservative part, so we can just deal with it. Like maybe if it's a closed curve, this part's going to integrate out to 0. If it's not, we'll just do f of the endpoint minus f of the start point. And this one, OK, fine, we have to do something with it. That's the idea. So let's try this for an example. So our question would be we're going to deal with this sort of complicated vector field for a little while now. So one question is this vector field conservative? OK, now I'll write down the vector field. So the vector field is 1 plus 1 minus 2y plus 2x e to the x squared y squared, comma, 2y e to the x squared plus 2x. Okay, there's our vector field, and we want to know that it's conservative because we're going to integrate it over a unit square, like a path. Okay, so one way we could do this is by trying to find a potential function for f. So we would integrate this part with respect to x, and integrate this part with respect to y, and see if we can get the same function somehow, cleverly. And we did that the last time, and now I'll show you a slightly different method to figure out if something is conservative. So if so, then f is the gradient of f for some function little f, which means that it's partial of f with respect to x, comma partial of f with respect to y. One trick you can use often is Clairaut's theorem. So Clairaut's theorem says that if you take the partial derivative of f with respect to x and then with respect to y, it's the same as if you take the partial derivative of f with respect to y and then with respect to x, assuming that f is a nice enough function, which our functions always are. So in this case, we could take the derivative of this with respect to y and the derivative of this with respect to x, and they should be equal. So, if f is conservative, if you call this p comma q, just the two components as we usually do, the partial of p with respect to y should be equal to the partial of q with respect to x. So this is an easy, so usually derivatives are easier than integrals. So before we checked if it was conservative by integrating both parts. Now we can check if it's conservative by just taking the derivative of both parts. Another way of saying this, by the way, is that 0 equals qx minus py. And you might recall, we're doing a recall again, that's also dangerous, that if f is completely in the xy plane, then it's some function p of x and y and some function q of x and y, comma 0. So now this is just some vector field in the plane. Maybe it's like negative x, negative y, comma x. Then the curl of f, if you compute it, you will get 0, 0, qx minus py as the curl. So I'm skipping this step, but it is something that we've actually done before. And so if f is conservative, this is equivalent to, so this happens exactly when the curl of f is 0, 0, 0, or just 0 vector. So a vector field is conservative when its curl is 0. And this is something that we computed algebraically a week or two ago, that if a vector field is a gradient vector field, the curl of a gradient vector field is 0. And it makes sense geometrically because, again, if you have curl in a vector field, it kind of means that the vector field is spiraling around, or circling around in some place. And so it's telling you that if you follow the vector field and you come back to where you started, your elevation will have increased, which doesn't make sense. So if it's a gradient vector field, the curl is 0. Okay. So this is a way that this is a trick that we can use to check if a vector field is conservative. So let's see if f is conservative. So if f is conservative, what is it? Py equals qx. So let's check. So that means the derivative with respect to y of the left side, which is 1 minus 2y, plus 2x e to the x squared y squared equals, we want to know, is it equal? Is it to the derivative with respect to x of the left side, which is 2y e to the x squared plus 2x. Okay, let's check. We want to know. Okay, the derivative with respect to y of the left side. Derivative with respect to y of 1 is 0. Derivative with respect to y of negative 2y is negative 2. And the derivative with respect to y of this whole thing, it looks complicated, but this whole first part is a function of x. So it's just 2y times this thing. So 2y times 2x is 4xy e to the x squared. Okay, we want to know, is it equal? Is it to the derivative of this thing? So this 2y is just a constant. 2y times 2x is 4xy e to the x squared plus derivative with respect to x of 2x is 2. Okay, we want to know if these things are equal. They're not, yeah? They're not. But check this out. So parts of them are. So let's see, maybe I should use red and green for the happy part and the sad part. So the happy part is that this complicated part here cancels out with this complicated part here. Yes! But this part here doesn't cancel out. Okay. So the idea is that we're going to write f as a conservative part and a non-conservative part. So let's try this. The part that was conservative, well, the one part was good, and this part here was good, and this part here was good. But this negative 2y part, not so good, and this plus 2x part, not so good. So let's write f as this part that turned out to be conservative, so 1 plus 2x e to the x squared y squared, comma, 2y e to the x squared, plus the part that wasn't conservative, negative 2y, 2x. So these were our conservative parts, and these were our not conservative parts. We shouldn't be too surprised that this negative 2y comma 2x wasn't conservative, because after all, that's basically our favorite example of a non-conservative vector field, just our counterclockwise circulation vector field. Okay, so this part is conservative. And you can try to find a function whose derivative with respect to x is this thing, and whose derivative with respect to y is this thing. For this sort of complicated part, let's see. This equals the gradient of f for f of xy is, okay, let's do this complicated part. I think it's just e to the x squared times y squared. Does it work? You take the derivative of this thing with respect to x. You get 2x e to the x squared times y squared. That works. Take the derivative of this thing with respect to y. We get 2y e to the x squared. Okay, that works. And then we have this extra 1 here. So we want something where the derivative with respect to x gives us 1. So I think we should add x. And then when we take the derivative with respect to y of x, it goes away. So there's our function. And then this part, okay, this is not conservative. So we broke it into a conservative part, which is easier to work with, and then this other part, which we'll have to actually integrate it. Okay, so here's a problem. Compute the integral over the curve C of f dot t ds for C, the counterclockwise unit square. So our curve is, I take the unit square, so start at 0, 0. I call it the unit square. Maybe that's not standard terminology, but that's what I like to call it. You go over here to 1, 0. Then you go up to 1, 1. Then you go to the left over here to 0, 1. And then you go back to where you started. So our curve C is this counterclockwise unit square here. Okay, there's C. And f is just the same f as we have just been talking about. Okay, so let's do it. Okay, so the line integral over C of f dot t ds, well, that's the line integral over C. I've written f in 2 parts here. The first part of f is the gradient of little f, where f is this function we came up with over here, plus, okay, this part that wasn't conservative, negative 2y, 2x. And we want to dot that with t ds. So this whole part here is our f, which we were able to break into a conservative part and a non-conservative part. Okay, so this is just a dot product. It distributes over addition. So let's break this into 2 parts. This is the integral over C of the gradient of f dot t ds plus the integral over C of negative 2y plus 2x dot t ds. Okay, so the way I'd like to think about this is that maybe this vector field is like difficulty of hike. And this curve, you're doing this curve, this hike here. Sorry that it's such a boring square curve. And the difficulty of hike is based on 2 things. One part of the difficulty is because you're doing elevation gain and loss. Right? It's hard to hike when you're going uphill. It's easy to hike when you're going downhill. And that's the part that is this gradient of f part here, because f is our elevation function. On the other hand, the other thing that makes the hike hard is that there's wind. There's this counterclockwise wind swirling around. So we break the integral of hardness of hike into the amount that comes from elevation gain and loss plus the amount from the wind, which isn't conservative. And we'll just compute them separately. So this is like elevation part, and this is like the wind part. Okay, so how about this? Here we're integrating a conservative vector field over a closed curve. Comes out to 0. Yeah, because we're starting and ending in the same point, or your elevation comes out to 0 if you do a loop hike. So this part is just 0 because we're integrating a conservative vector field over a closed curve. Okay, and how about this part? So this isn't so bad. Negative 2y, 2x, pretty simple vector field. And we're just integrating over these 4 pieces. Not so bad, just 4 pieces to do. But let's not even do that. Let's try to apply Green's theorem so that we could just integrate over the interior and do it all at once in just one step. So let's check to make sure that Green's theorem will apply. So Green's theorem, can we use it? Now I've changed my color scheme because I wanted Green's theorem to be in green. Even though this is maybe the part that's not so easy, because we have to actually do it. Okay, so first of all, is our vector field continuous over all the places we care about? Yes, 2y and 2x, very nice continuous functions. Okay, is our curve closed? Yes, it is, it closed. And if we integrate over the region inside, let's call it D, and we walk along the curve with our left arm out, as our left arm over D, yes. Okay, so yes, we can apply Green's theorem, so let's do it. So this part is the double integral over D of q sub x minus p sub y dA. And this part here is p, and this part here is q. Okay, so this is the double integral over D. The derivative of q with respect to x is 2 minus the derivative of p with respect to y is negative 2 dA. I'm just not going to carry around the 0 anymore because 0 plus anything is 0. So this is the double integral over D. 2 minus negative 2 is 4 dA, which is 4 times the area of D. And it's a 1 by 1 square, so it's just 4. So it tells you that the net hardness of your hike based on the elevation gain and loss was 0. And net the wind helped you to this tune of 4. Because, let's see, if the wind was going along like this, along this piece and this piece, the wind was perpendicular to you. And then along these 2 outer pieces, the wind helped you a little bit. Question, yeah?
So, how do you know that using Green's theorem is going to simplify our integral in a way that's easy to solve? Because in this case, we were lucky enough that it was just 4 times the area of the closed region, and the closed region happens to be something beautifully geometric that we can find the area of. But if it's something else that's not.
Yeah, right. Sometimes Green's theorem might not make your life easier. It's very possible. So it's possible that just doing the line integral might have been easier. We tried Green's theorem, because if we can do it in one step, it would be nice. And as you say, it turns out that we're integrating just 4 over a region whose area is easy to find. I mean, it was contrived that way. But it's totally possible that if you applied Green's theorem, you might get something that was harder. Yes, it's very possible to construct examples where I'm like, integrate this function over this region. And you're like, I can't do it. I better use Green's theorem the other way and turn it into a line integral and do that. Sure. Yeah. Yeah. Okay, so that's a nice way to use conservative vector fields even when your vector fields aren't conservative. And that sort of concludes our integrating over curves. So now we change gears and we learn about surfaces. So we've been integrating over curves, and even sometimes our curve was like a part of the parabola y equals x squared. But when we integrated over it, we didn't just call it y equals x squared. We parameterized as a function of t, because that allowed us to turn our integral into a one-variable integral. We'll do the same thing for surfaces. So we can't just use surfaces like, oh, z equals x squared plus y squared, a paraboloid. No, we'll have to parameterize it. So we'll now talk about parameterizing surfaces. So this is exactly analogous to what we've done with curves. So to describe a curve in the plane, any curve in space, you imagine the curve in space is like a fly buzzing around. And at any time t, you just give you the x, y, and z coordinates of the fly. So we call that little x of t, which is x of t, y of t, z of t. And that gives the position of the fly at time t. This has only one variable in it, so it's a one-dimensional thing. So this has one variable. So it's a one-dimensional thing. It's a curve. Another way to think about it, okay, so you're used to thinking about it as a one-dimensional thing as a curve. Another way of thinking about it is you take the number line, and this tells you how to take the number line and put it into space. So you're taking the number line and you're picking it up and curving it in some way into space to give you the path of the fly. So here's where the analogy comes in. So any surface in space can be described by big X of two variables now, s and t, as x of s comma t, y of s comma t, z of s comma t. And this has two variables, s and t. So this is two variables. So it's a two-dimensional thing. And it's a surface. So one way to think about this is that you're taking the plane, like the ST plane now, which is just like the XY plane with a different name, and just picking it up and curving it into space. So that's what's happening. So let's do some examples. So the first example we'll do, I'll give you a parameterized surface and we'll figure out what it looks like. And the second example, we'll figure out how to parameterize a surface. So for example, I think I'm gonna change it because I don't think we have enough time to do all three examples. So I'm gonna make this into the cone, which is on the back side of your sheet. We will survive somehow. So sketch the surface described by x of r comma, let's see, s comma t is, how about r comma t? So is r cos t, r sine t, r. Okay, so this is our surface, and now we're supposed to figure out somehow what this looks like. So here's some ways to do it. One way to do it is just to look at it and be like, ah, I know what it is. But this is maybe kind of hard. So let's think about a systematic way of going about it. So one way to do it is to fix one variable and then think about what the other variable looks like. So for instance, suppose we so fix r and vary t. Okay, so that means you pick your favorite value for r, maybe like r equals 5, and then figure out what this looks like. So let's say r equals 5. We get 5 cos t, 5 sine t, comma 5. So this is a circle of radius 5 going around. As t varies, it goes around, cos t, sine t, going around. And it's up at a z value of 5. So this tells us here, this is a circle of radius 5 at z equals 5. How about if, let's say, r equals 2, then we get 2 cos t, 2 sine t, 2. So this is a circle of radius 2 at a height of 2. So here it's a little bit smaller, and it's at a height of 2. So there's 2. And if you have r equals 0, you just get what? 0, 0, 0. So a single point. So maybe you can see that as you vary r, you get these circles that get bigger as you go higher and lower and in a linear speed. So you get a cone. Okay, it's supposed to be straight lines, but okay. So we get a cone. So this gives us a cone. We got that just from fixing r and varying t. Let's see what happens when we fix t and vary r. So now we'll fix t and vary r. So if you fix t, let's say, for instance, t equals 0. Cosine of 0 is 1. So we will get 0. And then sine of 0 is 1. No, sine of 0. All right. What did you say? Let's see. Cosine of 0 is 1. So r times 1 is r. That was correct. Sine of 0 is 0. R times 0 is 0. And r is r. So we get something that goes out a distance at r in the x direction and up a distance r in the z direction, and y doesn't change. So this is actually like some line here. So there we go. There's one of the lines. And if we did, say, t equals pi over 2, I believe we would get 0, comma r, comma r. So that would be some line like in the back, the line in the back. So this fixing t and varying r would just give us all these lines around the cone. Yeah? Yeah. So the idea is what's happening is that we have the r theta plane. Let's see. Here's theta. And theta is going from 0, let's say, to 2 pi. And then our r is going, let's say, from 0 to 5-ish, or maybe 6 if we're up here. And if we fix r and vary t, so as t, same as theta, fix r, that means you're keeping a specific r and letting you have all the t's. So you're going all the way around like this. On the other hand, suppose you fix t, so we pick our favorite t, like maybe this one, and we vary r, we get all of this kind of lines. So this is the picture in the RT plane. And then our parameterization takes this RT plane and picks it up and bends it into a surface. So you can think about what's happening is, well, first, if t is 0, t being 0 and t being 2 pi, they're basically the same because you're on a circle. So we take this and we fold it up into a cylinder. So our cylinder has pink lines going vertically and then white circles going around horizontally. And then we sort of pinch the bottom and flare out the top. So this is exactly how we take this, and this parameterization takes this and brings it up into space. First maybe turns it into a cylinder and then pinches the bottom and flares out the top. Pretty neat, right? Pretty cool. Yeah. Questions or ideas? Okay, so one thing we saw with curves is that there's many ways to parameterize the same curve. So if you have a bug that's flying on a certain path, you could also parameterize the same path by making the bug go faster, or making the bug go at a constant speed, or making it go like fast and then slow, and then fast and then slow and fast. It would trace out the same curve. And in the same way, we can parameterize a given surface in many different ways. So let's just do that by thinking about different ways we could parameterize a sphere. Okay. So let's parameterize a sphere of radius r centered at the origin. This is our quest. Please parameterize the sphere of radius r centered at the origin. Okay, let's draw a picture. Here's the picture, sphere. Here's the origin, and there's our radius r. Okay, so maybe our first idea, let's see. So first idea might be that, well, a sphere of radius r, that's just x squared plus y squared plus z squared equals r squared. So then we could solve this for z. Z squared is r squared minus x squared minus y squared. So z is square root plus or minus the square root of z minus of r squared minus x squared minus y squared. So what this would say is if you pick any point x comma y here, you can figure out what the z value is. It's there or down there. So our parameterization would be x of x and y would be x comma y comma plus or minus the square root of r squared minus x squared minus y squared. And then you want to say which values you want. For instance, we wouldn't want to have an x squared that was bigger than r squared, because then the square root wouldn't make sense. Where x and y are in the disk of radius r. Fine, but there are a couple things I don't like about this. First of all, there's this square root, which is ugly. Secondly, there's this plus or minus square root, which actually I'm not sure what to do about. I don't think we could actually do it this way. We'd have to parameterize the top and the bottom separately. And then the next thing that's bad is that we say x and y have to be inside the disk of radius r. I'd really be much happier if my x and y bounds were constants. So this is maybe not so good. So let's have our second idea. Probably you wouldn't have thought of that anyway. Rectangular coordinates and spheres do not play well together. So maybe our second idea is cylindrical coordinates. So then x of r comma theta will be whatever x is. I guess it's r cos theta. And whatever y is, r sine theta. And then whatever z is. Okay, so now we have different coordinates. This point now is r comma, that didn't go to the origin, r comma theta. And then we want to figure out what the z is. But we have the same problem. There are two different z's for any point in the plane. So this will be square root of big R squared minus little r squared. So that's still bad. Oh, plus or minus even. Even with a plus or minus, because there are two of them. But this is slightly better because we know theta has to go from 0 to 2 pi, and r has to go from 0 to big R. So that's a little better. We still have this ugly square root that we don't like, but at least our variables are our bounds on our variables are constants. So last, I guess I'm trying to do this in like first place, second place, third place colors, but I think I got them wrong. I think second place is red. Anyway, the best idea, the blue ribbon best idea, is to use spherical coordinates. So let's do x as a function of phi and theta. So this is, let's see. I try to remember what the z-coordinate is. The z-coordinate is rho, which in this case is just big R, times cosine of phi. And then the other ones, the x is r times sine of phi, and the y is r times sine of phi. That's like our radius, and then we multiply by here cos theta and sine theta. So that's just spherical coordinates converting back to rectangular coordinates. This is looking nice because there aren't any square roots or plus or minuses. I mean, or like two options. Everything's good. Let's figure out what our variables are. So we want phi to go between something and something. We want theta to go between something and something. I think theta needs to go all the way around, so 0 to 2 pi. And then phi, we want it to go from the North Pole, where the angle is 0, all the way to the equator, where it's pi over 2, all the way to the South Pole, where it's pi. So this has to go from 0 to pi. And suddenly this is nice, because theta is between constant bounds and phi is between constant bounds, and our thing is just all functions without any square roots or plus or minuses. So these are all different ways to parameterize a sphere. They would all work maybe for different applications, but this is probably the nicest one. Yeah? The frowny face is next to this one? Oh, maybe the frowny face should not be next to this one. The frowny face should maybe be next to the other two, because this is a happy one. Probably I meant to do a smiley face. Yes, this is an error, a horrible error in your sheet. Could you please turn that frowny face into a smiley face? Okay. Yeah, turn that frown upside down. So what is happening here is that let's see, theta equals a constant is giving us lines of longitude. So things like this. So these ones that are on the front and also the ones that are on the back, which I won't draw. So these are theta equals a constant. So here's theta. It's going all the way from 0 to 2 pi. And then for the phi axis, we're going from 0 to pi. Those give us longitude lines. So if phi equals pi, we're up here at the North Pole. If phi equals 0, we're down here at the South Pole. And then for phi equals pi over 2, we're here at the equator. And then for the other lines, there's the other latitude lines. And then the ones on the top. So what this parameterization is doing is taking a rectangle, a 2 pi by pi rectangle in the theta phi plane, and turning it into this. So you can imagine, again, that you take 0 and 2 pi. Those are identified. So you turn it into a cylinder, which has vertical white lines and then these purple circles that go around. And then you pinch the top and the bottom and turn it into a sphere. So that's what this parameterization is doing. Yeah. Okay. Okay, the last thing we should talk about is that when we have surfaces, we often care about the normal vector. So when we first studied surfaces a month or two ago, we cared about the normal vector because we wanted to make a tangent plane. And if you have the normal vector to its surface, it's not too hard to make the tangent plane because you can pull the coefficients of the tangent plane right out of the normal vector. Here, we want a normal vector because it will help us to integrate vector-valued functions over our surface. So the idea is that suppose you have a vector field, like maybe this is a wire mesh sphere, and you're holding it out in the wind, and the wind is going through your wire mesh sphere. So in some places, so here, the wind is going like this, maybe like that, and you want to know how much is the wind going through my surface. Right here at the bottom, where the vector field is going the same direction as the surface, I would say the vector field isn't going through your surface at all. It's just going along your surface. But here, I would say actually your vector field is going through your surface quite a bit because it's just passing right through the surface. And the way you can measure that is with a dot product. So if you take the normal vector to the surface, so here's a normal vector down here, maybe here's a normal vector here, here's a normal vector here, here's a normal vector here. You can take n dot f measures how much the vector field points through your surface. Let's say flows through your surface. So down here at the bottom, where they're perpendicular, the dot product of these two things would be 0. And in fact, so that makes sense. It's not flowing through at all. But up here, where they're pointing the same direction, the dot product would be quite big because the vector field is flowing right through the surface. So that's why we're going to care. So we want to find, this is something you should not abbreviate on the board, normal vector to a surface. Okay, good? Good, okay. So we want to find the normal vector to a surface. So our way for planes was that if we had some plane and we wanted to find the normal vector to the plane, that was our dream, well, we took two vectors that were in the plane. So here's vector 1 that lives in the plane. And here's vector 2 that lives in the plane, or is parallel to the plane. And we took their cross product to get the vector that was normal to the plane. So n was v1 cross v2. Because the cross product of two vectors is perpendicular to both, so n is perpendicular to v1, and n is also perpendicular to v2, so it's perpendicular to the plane. That's what we did. So our idea here is to find two vectors tangent to the surface, and then find their cross product. So normal vector will be their cross product. And here's how it works. So we just need to find two vectors that are tangent to the surface. Here's the brilliant idea. The first thing, let's say we want to find the normal vector right there. The first one you do is a vector in the direction of the purple. So if you hold phi constant and you vary theta, you would get something in the direction of the purple. So that will be this vector, which we will call, I'll make a space for it so you can see it, x sub theta. Because this is what happens when you hold phi constant and vary theta. So here, the first vector is going to be x sub theta, the partial derivative in the direction of theta. The other vector is going to be the one that's in the direction of the white. So that one is x sub phi. So x sub phi. Nope, that's not a phi, that's a theta again. And then we'll want to take our cross product, so n will be x sub theta cross x sub phi. And that will give, since it's perpendicular to both, this normal vector n that's perpendicular to both. That's the idea. Okay, so let's try it for the cone, since we've already parameterized it. On your sheet, you have doing this for the sphere, which has a lot of variables in it. So you can read it, but I won't do it on the board. So let's find a normal vector to the cone. And our cone was x of r comma t was r cos t, r sine t, r. Okay, so the first thing we need to do is take the partial derivative with respect to r, okay, or t, doesn't matter. Let's just partial it with respect to r. So partial of x with respect to r is cos t sine t 1. Let's see what this looks like. So here's our cone. And we have some point on it, r cos t, r sine t, r. And we're holding theta constant and varying r. So if we have some point on the cone, so I'll just put on in a few things here so that you can see what's going on. So if we hold theta constant, that means we're not going to go around the circle at all. We're just going to see what happens when we increase r. So this would be this direction. So this is x sub r. On the other hand, we can also do derivative of x with respect to theta. So this is if we hold theta constant, if we hold r constant and vary theta. So we won't be moving up or down the cone at all, we'll just be going around. So we expect to get a vector kind of in that direction, which is now hard to see because xr is in the way. Okay, so here's going to be x theta. This was xr. Okay, so x theta, derivative of these things with respect to theta, is negative r sine t theta t, same thing. Negative r sine t, r cos t, derivative with respect to t of r is 0. So indeed, it tells us we're going around the circle and our z value isn't changing at all. Okay, so a normal vector is going to be given by xr cross xt. So we just do I, j, k. The components of the first one, cos t, sine t, 1. The The components of the second one, negative r sine t, r cos t, 0. And if you compute this out, you get, let's see, negative r cos t, negative r sine t, r. Okay, so we should figure out what it is. So take your right hand and put your fingers in the direction, I'm going to have to go on this side, of xr. Bend them toward the direction of x theta, and the cross product is in the direction of your thumb. So the cross product here is pointing in. So maybe it's a bit hard to see because it's going into the cone, but it's going in. So if you had a beautiful cone here, and you compute the cross product of the two vectors on the surface, you get a vector that points into the cone, perpendicular to the surface. And this, if you look at it, this is negative x, negative y, z, if you're at the point x, y, z. Okay, so this is a way to give a normal vector. And I should mention that for the cone, I was saying, oh, it's going into the cone. And for the cone, you have a natural idea of inside and outside. So here, the inside of the cone is white, and the outside of the cone is kind of purple. And the same for a sphere. You could have the inside of your sphere could be white, and the outside could be purple. But for some surfaces, like this Mobius strip, it only has just one side. If you tried to color one side purple, you'd find that the whole thing was purple. This strip, on the other hand, you could do one side purple and one side white. So that's called orientability, knowing which side is which. And we will only be working with orientable surfaces. All right, thank you.